Okay, we are at 19.7 Ampere's law. Um, so during an electric demonstration in 1819, Danish scientist Hans Ørsted found that an electric current in a wire deflects a nearby compass needle. Um, so let's share uh, this is what Ampere showed with no current in the wire. When no current is present in the vertical wire, all compass needles point in the same direction. That is the Earth's magnetic field. They're going to point along the Earth's magnetic field. When the wire carries a strong current, the compass needles deflect in directions tangent to the circle, pointing in the direction of B due to the current. Let me show that with a little Walter Fent demonstration. We won't spend a lot of time because it's really very simple. Okay, so now the plus and the minus here would be like the direction. In other words, the battery. The battery would be connected to the plus, and the negative side of the battery to the minus. So the battery would be going like this, and so the conventional current, the red arrow, is going in this direction, and the electrons are the little dots moving down. I don't even know if you can see those on the screen. But so that when the conventional current is this way, the magnetic fields that are produced are, it's a different right-hand rule. It's very similar to the magnetic moment. You point your thumb in the finger, you point your thumb in the direction of the current, and your fingers point, using the right-hand rule, your fingers point in the direction of the current. So you can see the conventional current, the red arrow is going up, so the circles go around this way. And you can see that if we move this magnet around, it's always tangent to the circle where the B field is. Now let's reverse the current. Now the current is going down, and using the right-hand rule, you can see that the blue lines, the magnetic field lines, are going around this way. And you can see that the compass has reversed. Okay, that's enough of the Walter Fent. And now let's continue on. So, okay, there he's describing the right-hand rule. Your thumb is in the direction of the current, and the B field is in the direction of your fingers. Your fingers point in the arrows that the B field is in. And there's a little physical picture of it next to it. So B, the magnetic field, is equal to mu zero times the current I divided by 2 pi r, where r is the radius, the distance that you are from the wire. So the closer you are to r, the closer you are to the wire, the smaller r is. The B field is greater, and mu sub zero is called the permeability of free space, and it's 4 pi times 10 to the minus 7 Tesla meters per amp. Tesla meters per amp. That's the mu sub zero. Okay, so B is the sum of the B, and it's parallel to all these little delta L's. These little delta L's that run around is equal to mu zero times I. Well, we expand that. Since B remains the same, we can pull it out of the sum. And so it's B times the sum of all these little delta L's. Well, what are all these little delta L's? Well, it's 2 pi r. It's just the circumference. It's the circumference of the circle. So B times 2 pi r is equal to mu zero I. Well, so B is equal to mu zero, the permeability of free space times the current divided by 2 pi r. That is what B is. Okay, and that's it for Ampere's law. All right, let's see if there's anything I missed. I think that's pretty Um, okay, this is for a constant current. This works for a constant current. All right, and the next we're going to talk about magnetic force between two parallel conductors. Uh,